Hello, everybody, and welcome. Here is coming our lovely seminar, prac seminar for mathematical physics, and I'm really glad that I can welcome Frederik Ďalak, who represents young blood in our mathematical institute. He's a first year PhD student under the supervision of Rano. And he did his master degree in the University of Bratislava, the Communist University, out of where he drew much attention from online audience, I guess. So this is the point when I would like to welcome our online audience from Bratislava. And Frederik was so nice that he prepared for us this nice talk. It's about the derivative of a linear connection, and he is going to show us some application of the data tree. So very looking forward to it. So it was my pleasure, and I think we can we can give you full control of upcoming 16 minutes.
Yeah, so thank you for the introduction. So can I just first figure out how to work the slides stuff?
Wait a second, I need to share screen and yeah.
Okay. So I just use the down.
Yeah, of course.
Okay, so.
That's very cool. It's somehow stuck completely. Sorry for these technicalities.
Everything is stuck.
Infinity stuck.
Infinity stuck.
I think device slowed down.
But the computer is moving, so it's
Really? Aha. You're right.
just mash some random buttons.
Try to read it out. Maybe they just has a trouble to load, but there are a lot of pictures in the presentation. Oh, nice. Easy. Oh. Thank you. Yes, so thank you for your introduction. And also, as it was mentioned already, the topic of my today's talk is going to be the derivative of linear connection and its applications. So this is actually the topic of my master's thesis, on which I worked supervised by Dr. Petsko in Bratislava. And oh yes, so as the name suggests, we are going to be trying to define a Lie derivative as an operator acting on linear connection on a manifold. And yes, so I'm sure you know we are familiar with the Lie derivative as an operator acting on tensor fields, but it's actually also possible to compute it for the case of linear connection. And so this idea is actually as old as the concept of the Lie derivative itself. Among the very first articles we started using the name of Lie derivative, there was also considered the possibility to compute it for linear connection, but this is much less known possibility, or at least for me, this was a new information when my supervisor told me about this. And so, yes, so I hope also we will be able to extract some kind of new information from my today's presentation. Also, let us start. So, our first step on our way to define actually the Lie derivative of linear connection is going to be to learn to compute a pullback of a linear connection from one manifold to another manifold using a diffeomorphic map between these two manifolds. And yes, this is going to be then serve us to define the Lie derivative itself also. So let us look at how this can be done. So we can first consider the following situation, that we would have two manifolds M and N, and we are considering also that there is a linear connection nabla present on the manifold N, whereas on the manifold M there is a priori no linear connection. And also we are considering a diffeomorphic map F going from N to N. Yes, and so what we actually mean when we say that there is a linear connection on N is that if there are a couple of vector fields on N, what we can do is we can compute a covariant derivative of one of these vectors in direction of the other one, which obviously once again results in a vector field on N. And now on the manifold M, there obviously also reside some sort of vector fields, but since there is no linear connection present here, it is not possible for them to compute the covariant derivative. And so we are going to sort of see this as a problem now and try to help them solve this problem. And based on what we see on this picture, we would like to come up with a way to also define the covariant derivative also on the manifold M. And so since there is the map F present between going from M to N, the first maybe clear step what we can think about is we can compute a push forward of both of these vectors and get their images on the manifold N. So now we end up with two vector fields. They are already on N, and so there is also a linear connection nabla, so we can also compute the covariant derivative for them here. And so this maybe moves us kind of one step closer to our goal, but this vector field is still clearly on the wrong manifold. So what we would like to do is to get it back to the manifold M. And so at this point, it is useful for us that the map F is actually diffeomorphic. So we can also compute a pullback of a vector field going backwards in the opposite direction of F, which is then just going to be defined, of course, as a push forward, but using inverse map to the map F. So yes, this is what we can do. And now we end up with a vector field on the manifold M. So this is clearly already a very good candidate for us for our definition for the covariant derivative on M, and also sort of a good candidate to introduce the linear connection on the manifold M. So this is going to motivate the following definition. We are going to define something we are going to call the pullback connection, and this is going to be a linear connection on the manifold M. We are also going to sort of denote it as a pullback of the connection nabla using the map F from the manifold N, and this connection is going to be defined using the following formula for the covariant derivative. So this basically just says that if you want to compute the covariant derivative corresponding to this pullback connection, what we should do, and if you want to compute it for a tensor T on M and in direction of vector V, what we should do is just take these two objects and we go with them through the procedure that we basically described in the picture. We just push forward both of these objects to N, then we can compute the covariant derivative and pull back the result back to the manifold M. Yes, and so it's actually quite easy to show that this formula actually satisfies all the properties which are required for it to be covariant derivative. So we can claim that we actually managed to make our first step, and we actually are successful in computing a pullback of a linear connection using a diffeomorphic map. So this is something we are going to be able to use when defining the Lie derivative for linear connection. And so let us look at how this can be done. So first of all, if you want to compute the Lie derivative of anything, basically, first thing you are going to need is a vector field u in direction of which you are going to be computing the derivative, and the corresponding vector field flow phi t, which for every value of the parameter t, this is an automorphism of the manifold M. And so here we can just use the analogy with the definition of the Lie derivative for tensor fields, which we already know what are familiar with, what it should look like. So if we have a tensor field T, and we want to compute a Lie derivative of T in direction of U, then what we should do in this case is that we take the vector flow phi, we use just an infinitesimal value of the parameter epsilon, and then we compute a pullback for this map of the tensor T. Then we subtract the origin of the tensor, and then we sort of look at the difference of these two results to the first order in epsilon. And so this, by definition, is the Lie derivative of the tensor field T. And so now if someone would like to define the Lie derivative also for the linear connection, And so maybe just the first naive thought that we would obviously think about is that we could just simply replace the words tensor field with the words linear connection and replace the letter T with the sign lambda denoting the connection, and we would be basically done. And so this sort of naive way of thinking sometimes actually pays off, because this is going to give us like at least a good sort of abstract definition of what we want to do. So let us just sort of abstractly define something we are going to call the Lie derivative of linear connection lambda in direction of u. And here we simply steal the notation. So what we do is we take the vector flow phi corresponding to the vector u. We take it for the infinitesimal value of the parameter, and we compute the pullback connection in the way which was described in the beginning. And then in some sense, we are going to take the difference between this connection and the original one, and we look at the difference to the first in the first order in the parameter. But so as I mentioned, this is still just a very abstract formula because we are not clearly able to imagine what it means to imagine or compute the difference between the two linear connections. But first of all, what we can look at, what we can realize is that unlike in the example in the beginning, here we are using as our diffeomorphic map to compute the pullback connection. We are using the vector flow phi, which is an automorphism of M, and therefore the new linear connection that we end up with is on the same manifold as the original connection, and therefore also the covariant derivatives corresponding to both of these objects. So both of these connections are obviously sort of expressed using their covariant derivatives, and both of these covariant derivatives act on the same objects, on the tensors, on the tensor algebra on M. And so we are going to be able to express this sort of abstract formula using these covariant derivatives. So we just once again start with this abstract definition, and what we do here is we express it in the language of the covariant derivatives. And so since the covariant derivatives is obviously an operator assigned to every vector field of the manifold, then what we get is also for the Lie derivative of the connection in direction of u, this object is also going to be assigned an operator, which is for every vector v, it acts on the tensor algebra on M, and we can see that it acts as a difference of the two different covariant derivatives to the first order in epsilon. Yeah, so this is going to be sort of our definition of the operator. And so here we should be a bit careful because there are two different vector fields in the definition of the operator, which have very different roles. So at least I was a little bit confused about this when I started working with this. So u on the left side here is the vector field in direction of which we are computing the Lie derivative of the connection. And on the right side, it is represented by the vector flow phi. And v is here just an arbitrary vector field on the manifolds to which we assign this operator. Yes, and so since, just give me a second. Since we sort of define the new operator acting on the tensors on the algebra, we'd also like to get a kind of specific formula which would tell us what specific actions are we supposed to perform on the tensor once this operator acts on it. And to obtain such a formula, it's actually just a short exercise about kind of relationship between operators. So we can just go quickly through it here. So we can apply this operator to an arbitrary tensor. We start from its definition. First of all, what we do, we express the covariant derivative for the pullback connection using its definition. So now there we get some kind of term with combination of pullback maps and push forward maps. And here, as I mentioned, the push forward can be expressed as just a pullback, just using the inverse map. So this is what we do first here. And now we get a term with pullbacks, where as a map we use the vector flow phi corresponding to the vector u. And this sort of pullback can be expressed as the exponential of covariant derivative in direction of u. So this is what we do next here. And now we get a term with different exponentials of the Lie derivative in direction of u. And so all that is left to do is basically just expand these exponentials and gather the terms to the first order in epsilon. And these are then, once epsilon goes to 0, these are going to provide our result. So what we end up with is that once we act with our operator on the tensor, we get these three following terms. So first of all, the first two terms represent some kind of a commutator of the lead derivative in direction of u and the covariant derivative in direction of v acting on the tensor t. And then we have a minus term where we act on t with covariant derivative in direction of the lead derivative of v in direction of u, which is just a commutator of u and v, obviously. So basically, this is our formula that we obtain for our operator. Okay, so once again, this operator is going to tell us about the difference of action of the two different covariant derivatives on the tensor algebra. And so it is also somehow a way to work more specifically with the concept of the lead derivative of connection, unlike the sort of abstract definition that we started from. And so now that we are kind of more clearly able to imagine what it means to compute the lead derivative of connection, we can proceed to look at the symmetry of linear connection. And so in general, the most common way to use the lead derivative is that you are interested in symmetries of the objects that you are studying, of which you are computing the lead derivative. And this is done obviously in such a way that you are interested in vector fields in direction of which the lead derivative vanishes, because so these vector fields then form also the free algebra of vector fields, which generate such automorphisms of the manifold that preserve the studied object in some sense. And so here we are going to get Lie algebra of symmetries of linear connection. And so in the next part of the presentation, we are going to look at what is sort of valid for these symmetries, and also why are we interested in them, sort of their geometrical interpretation. And we are also going to obtain an equation, a formula to look for these symmetries in a specific case for a specific linear connection. Okay, so we can just start with the condition for the symmetries. So once again, if u vector field u is a symmetry of linear connection nabla, then the lead derivative has to vanish, which in the language of the operator, this just means that the operator has to vanish. And so of course it has to vanish in direction of arbitrary vector v, and it has to vanish when acting on the whole tensor algebra. Now here we can just remind ourselves of the definition of the operator. So it is defined once again as the difference of the two covariant derivatives. And now that we are considering the symmetry u, then the operator has to vanish, which just gives us 0 on the left. And this just leads to the fact that for a symmetry, the two different covariant derivatives are actually going to be the same. So once again, just expressing the covariant derivative for the pullback connection by its definition. So this is kind of a valuable formula that is going to be valid for the symmetries that we will be able to work with. And so sort of what we have done here is that on a manifold where we already have a linear connection, we came up with a formalism that allows us to introduce different linear connections on the same manifold. But what we are seeing now is that, in fact, mostly we are interested in that case where the formalism leads to the fact that the two different connections are actually going to be equal. Because obviously when we have a linear connection on a manifold, it has some kind of maybe geometric or physical meaning for us. And so we are not actually looking to replace the original connection by a different one, but rather we want to learn something about the properties of the connection that we already have there. So, and this is what the symmetries are going to allow us to learn. So yes, this is going to be our focus moving forward. So once again, as I mentioned, we can start from the useful formula given by the equality of the two different covariant derivatives. And once you just sort of reshuffle the terms in the formula, you can get it into the following form. And so this just tells you that if you have the automorphism, the vector flow corresponding to a symmetry vector, and you act with it, and you compute the pullback from it, and you act with it on a term given as a covariant derivative of t in direction of v, then what happens here is that the pullback sort of jumps over the covariant derivative, and it acts kind of separately on the vector v and separately on the tensor t. And this is something we call the natural behavior of the pullback with respect to the covariant derivative. And this, as we are going to see, is going to be quite useful, especially once we consider geodesic curves on the manifold. So what it means to say that gamma is a geodesic curve on a manifold M with a connection nabla is that here I consider the finely parameterized geodesic, And so what it means that if we compute the tangent vector to the curve gamma, and we compute the covariant derivative of this vector in direction of itself, which will give us 0 for the finely parameterized case. And so now we can once again consider a symmetry and compute the pullback with respect to the automorphism coming from a symmetry and pull back this equation. In fact, here we are using push forward, but as I mentioned, these are sort of interchangeable terms when it comes to the vector field flow. So also the push forward method is going to exhibit the natural behavior with respect to the covariant derivative. And so it also jumps over the covariant derivative. And what we get is we get just a similar equation to the one which we started from, but instead of the tangent vector to the curve gamma, we now have the push forward of the tangent vector to the curve gamma. And so this is nothing else but if you want to compute the push forward of this tangent vector, what you have to do is you just take the curve gamma, then you sort of shift it using the transformation, and then you compute the tangent vector to the shifted curve. And so what we find out here is that if the original tangent vector satisfies the geodesic equation, then so does the shifted tangent vector. And therefore, if the original curve gamma was geodesic, then also the curve transformed by the symmetry is also going to be geodesic. And therefore, the symmetries of linear connections are going to correspond to such maps or such automorphisms of the manifold, which map every possible geodesic on the manifold onto another geodesic. So they are going to sort of preserve the geodesic curves in this sense. Yes, so this is going to be kind of the geometrical meaning of the symmetries. And yes, so once we have learned about the geometrical interpretation, we can also proceed.
Yes, question, and is the converse also true? So if you have some vector field such that its flow preserves all the geodesic, is it true that it's a symmetry? Or?
For a finely parameterized case, yes. There are projective transformations which also preserve also the non-finite. So once again, if something is a vector field flow corresponding to a symmetry, it preserves all the finely parameterized geodesics and also the non-affinely parameterized, but it's it goes backwards only for the affinely parameterized case. So yes.
Okay.
Okay, so yeah, this is going to be the geometrical sort of interpretation of the symmetries that we are going to be able to find. Yes. And so now that we know about the geometrical meaning, we can also proceed to try to find actually an equation which would allow us to find these symmetries in some kind of specific case. So basically, if we are given a general linear connection, we would like to have an equation which, for this case, is going to allow us to find the symmetries corresponding to it. And so since the linear connection is represented obviously first by its covariant derivative, and then there is two sort of objects, the curvature tensor and the torsion tensor, which sort of describe the corresponds to the linear connection. And so these are perhaps the objects in the language of which we would like to have our equation. And to obtain such a formula, we can start by introducing a vector field, sorry, a tensor field of type 1, 2, corresponding to the derivative of linear connection. And it is possible to define it in the following way. So I did not really get the L nabla U tensor because it's tensor fields which corresponds to the derivative of the connection nabla in direction of the vector U. And so as I mentioned, this is a tensor field of type 1, 2, which means you can fill it with two vector fields x and y, and one form alpha, covector alpha. And how it's defined is that you take the operator of the derivative of connection in direction of u. Then this operator is expressed in the direction of the vector x, and it's applied to the vector y. And this once again gives you a vector field, and you insert this vector field into the one from alpha. And so this can be actually, it's usually shown that this guy is linear in all the three slots. So it's a well-defined tensor field. And especially once we consider now a symmetry vector u, then the operator is always going to vanish. And that is going to lead to the fact that also the tensor field is going to vanish. So to say that u, vector field u, is the symmetry of the linear connection nabla is the same as to say that the L tensor field is going to vanish for the given vector u. So in the language of the vanishing of this tensor, we are going to be able to formulate our equation for the symmetries. And so this this tensor field, once you play around with the definition, it can be actually expressed using the curvature and the torsion corresponding to the connection. And to do this, we can introduce two quote-unquote new tensors, but it's actually just kind of renaming the curvature and the torsion tensor. So first of all, we introduce a tensor field named RU, which is nothing else but you take the vector u and you insert it into the curvature tensor in the second slot, which gives you a tensor field of type 1, 2. And then when we can introduce a TU tensor, which is nothing else but the torsion tensor, and the U is inserted in the first slot here, which gives you a 1, 1 type tensor. And then once you play around with the definition, you can express our tensor field for the linear derivative of connection in the language of these three terms. So first of all, you take the vector u and you apply twice the covariant gradient to it, which gives you a 1, 2 type tensor as it should. Then you add the RU tensor and then the covariant gradient of the TU tensor, which once again this gives you type 1, 2 tensor fields. And so yes, this is going to be the linear combination of these k terms has to vanish in order for U to be the symmetry of the given linear connection nabla. And yes, so this is going to also allow us to compute the symmetries for some kind of specific case. And as we can see, it's also quite useful formula because it also allows us to sort of distinguish between the influence which the curvature and the torsion for the corresponding connection has on the condition for the symmetries of the connection. Yes, and so now that there is an equation which allows us to compute the symmetries, we can also look at.
May I have a question?
Yes, of course.
To the next slide. Is it anyhow obvious when I look at equation 15 that this is of tensorial nature?
So the covariant gradient maps a tensor, certain tensor to a tensor of type. Like you add one more vector field slot.
Yeah, so you end up having
yeah, so I believe the 13 and 14 definitions are fully tensors, and you just yeah, so this is actually not the same as the second covariant derivative of U. You know, it's, you apply the first covariant gradient, and then you get a 1, 1 type tensor, and then you apply another covariant gradient to that object. So yes, so yes,
it's yeah obvious.
I believe it's more or less yes.
Okay.
Yes.
Sorry, you can see it was a question. Usually, so in Formula 12, is it up to shows that it's tensorial with respect to y? So if you multiply y with this most function.
Yeah, yes, that's the toughest one to show, but it's yes, basically. So it's actually maybe even easier to show when you just take the coefficients and the difference of yes.
Okay.
Because by definition, it's the difference of two connections.
Yes.
Okay.
Or is it visible from the formula that you described, actually, the fact that it is tensorial?
Oh, yes, you can.
Either from definition, yeah, or from the formula you gave up to 3 slides.
No, let me see.
Sorry for.
You mean?
No, or no.
Yes, you can start. You can start from. Yes, you can start from this side. Let's show it. Yes. It's pretty straightforward. Yes.
In particular, the derivative of connection is not a connection.
Yes, exactly. So also the operator is also not the covariant derivative itself. It's just. Yes. So now that we have the formula for symmetries, we can proceed to look at sort of specific example how to use this. And here I chose actually quite simple example from physics. In fact, the physical situation we are going to be describing is just the Newtonian gravity, just formulated in a sort of geometric way. And the reason why I chose this example is that we are going to be able to recover a very familiar result, but in a sort of new and fun way. And I believe this is a nice way to show how this formalism may be useful for you to learn something interesting about your theory if linear connection plays a significant role in yes, the theory you are describing. So yes, let us start. As I mentioned, we are going to be just describing the Newtonian gravity, but a geometrized version of it, sort of. And the corresponding theory is called the Newton-Cartan theory. So maybe I can give you a little bit of background if you are not familiar with this. So this is something Cartan came up with in like early 1920s-ish. Don't quote me on that, but it was around this time. And so in this period, he was obviously very impressed by the Einstein's work of general relativity, where he was able to geometrically describe the relativistic gravitational phenomena. And so Cartan wanted to see if he would be able to also geometrically describe the classical Newtonian gravity. And more specifically, he wanted sort of to copy the Einstein's idea, or the idea of general relativity, and to introduce a curved Newtonian spacetime in which the trajectories of moving massive objects would be given by geodesics in this curved Newtonian spacetime. Or in other words, he wanted to introduce a linear connection in such Newtonian spacetime, which would lead just to the fact that the trajectories of moving massive objects would be simply geodesic curves in this Newtonian spacetime. And so here we are going to look at just a very simple version of this Cartan's theory. We can consider a four-dimensional spacetime manifold with four coordinates x mu. We are going to use index notation from relativity, where the zeroth coordinate is going to be the time coordinate. But here it is the absolute Newtonian time, which flows everywhere the same in the universe and all this stuff. And so clearly, the trajectories of points of massive objects in this spacetime are going to be represented by curves in this spacetime. And since there is the Newtonian time is the zeroth coordinate, it's going to be natural for us to parameterize these curves directly by the Newtonian time at the zeroth coordinate. And this is going to lead to such trajectories of moving massive stuff that along these trajectories, always the derivative with respect to the parameter of the zeroth coordinate is going to give us 1, and the second derivative of the zeroth coordinate is going to vanish, because these are obviously just derivatives of time with respect to time. And so in such spacetime, Cartan had a very simple idea. Actually, he knew that the trajectories of massive objects are simply given by the Newtonian equations of motion, where we just say that the second time derivatives of spatial coordinates along these trajectories are given by minus gradient of gravitational potential. And he wanted to make sure that these trajectories are geodesics. So he proposed to look for such linear connection, which just leads to the fact that the geodesic curves are simply going to be equal to the equations for the geodesic curves are going to be equal to the Newtonian equations of motion. And so more specifically, he wanted to look for such coefficient of connection, which simply lead to, to the fact that these two sets of equations become the same set of equations. So he considered this condition 17, and moreover, he considered the condition of vanishing of torsion. So he was looking for a torsionless connection. And these two conditions then lead to a uniquely defined linear connection in the Newtonian spacetime given by these three non-zero coefficients of connection, and the rest of them vanish. And so these are given, as we can see, by some kind of spatial derivatives of the gravitational potential. And so when you look at the three equations on this slide, it's easy to make sure that it's actually satisfied that Cartan was successful in making sure that the geodesic equations become just the Newtonian equations of motion. And so now we are going to look at the symmetries of this sort of Newton-Cartan connection. And since as we saw, the symmetries correspond to such automorphisms of the manifold, which map geodesic curves always to another geodesic curves. And since here the geodesic curves are the trajectories of massive objects, then the symmetries of this Newton-Cartan connection are going to be such transformations of the spacetime, which always map each possible trajectory onto another possible trajectory always. So this is going to be then be the sort of physical interpretation of these symmetries that we find. So let us look at the condition for symmetries. since we are dealing, as I mentioned, there with the torsionless connection, the third term corresponding to torsion is just going to vanish, and our formula for the tensor of Lie derivative of connection is just given by these two terms, which leads to the following set of equations, which are just obviously the equations for components of the tensor for the Lie derivative. And now we can just pick a very simple form of the gravitational potential. We are going to consider a spherically symmetrical potential given that just by the mth power of the radial coordinate r. And yes, let us now compute these equations for this gravitational potential and look at the Lie algebra of symmetries for this specific Newton-Cartan connection. And so first of all, in the Lie algebra of symmetries, we are going to find the vector partial t, which obviously generates the time translations, which is very predictable outcome because we are considering clearly the time independent potential, so you can freely move the solutions of trajectories in time. Then there are going to be rotations, which once again is very predictable for the spherically symmetrical potential, so you can just take the trajectory and move it around the spatial center of coordinates. And then there is this one more symmetry vector. As we can see, this it's given as this formula, and it also depends on the value of the exponent in the gravitational potential. And it says, as we can see, 1 minus m half t partial t plus r partial r, where t partial t vector is such a vector field which points that much more in the time direction the further you go in time, so it's going to sort of inflate the space-time in the time direction, and in change the r part is going to inflate the space-time in the spatial direction. So this guy is going to sort of inflate the space-time at some rate in the time direction and at a different rate in the spatial direction. And so to figure out what this actually means, we can pick just a very simple high school version of the gravitational potential by picking m equals -1. This just gives us the potential around the huge massive body. And for this case, the vector just says 3/2 t partial t plus r partial r. And so the corresponding transformation of the manifold, the vector with flow, I called it here psi lambda. And this is going to map t to the e to the 3/2 lambda times t, and r gets mapped to the e to the lambda times r. And so for each value of lambda, this is supposed to be an inflation of space-time leading to preserving the trajectories. And so to visualize this, we can imagine just a trajectory like a moving planet in the space-time, which is given like by this sort of elliptic spiral in the space-time. And what this says is that we can inflate the spiral in the spatial direction, but only if we inflate it even more in the time direction. And so this leads to the fact that the planet moving along the bigger spiral is going to have to move more slowly along this trajectory. And you may have already been able to notice that this happens in such a way that the ratio of the square of t and the cube of r remains constant along this inflation of space-time, which is obviously just a sort of representation of the Kepler's third law of planetary motion. And so, yes, this is obviously not some kind of groundbreaking revelation, but it's kind of a new and funny way to verify the validity of a known result. And I believe it's a really nice way to show how this formalism may be useful for you to learn something interesting about the theory you are describing. Because when you think about the physical situation, the first two solutions of the symmetry algebra are very obvious. But the third sort of weird inflation of space-time leading to preservation of the trajectories, it would be harder to see up front. So yes, I believe this is a nice way to see how this can be useful for you if, for example, geodesic curves are important in your theory, as we saw here. Yes, and finally, I have included here a couple of articles in case you are interested in this topic and you would like to learn something more about it. So maybe this is something you would like to look at. And yes, thank you for your attention.
Thank you very much. This was a really insightful revelation of symmetries already before, but this is time for our questions, so please.
In the Kepler case, the symmetries you displayed a formal group.
Lie group.
Yes. So
And,
the vectors formally algebra, yes, and
Yeah, and sometimes this is called, if I write conformal group. Conformal group, which is sometimes SO, a certain subgroup of special orthogonal, special orthogonal group of signature 1 and +1.
I am not familiar with something like this.
Yeah, this can be visible, but probably. But my question is, what in further dimensions you were displaying there is U, which is dependent on M, T, and R. So what does it do in further dimensions? Have you checked that?
Oh, I have not actually. No.
In dimension 3, it was making the spiral expanding, making the spiral, the helicoid expand.
So it's quite some time since I was dealing with this, but I believe it would work in higher dimensions. Something we should get something similar.
Let's think for this potentials are to the power -1 to such for symmetry.
Yes, it definitely could be interesting.
There are simple groups or simple groups times semi-direct products, something nice out there.
Yes. So I'm not sure about the answer. Sorry.
But it's quite popular at the institute is that there are people searching for Dirac operators. They have the Maslow's equation for Dirac operator has more symmetry than just the Lorentz Poincare group with the special orthogonal, but also you can multiply with some conformal invariants, which can be represented either in two ways. Dilations, rotations.
Yes, I remember.
Also, reversions with respect to circles, inversions. And or by some so-called parabolic subgroups of SO with some specific signature, special orthogonal specifics. So it will be interesting, but also in higher dimensions for the potential R to the power n-1, this group arises, which the potential is somehow unphysical. It should be actually R to the power 1 minus n. The solution of the Laplace equation. Maybe not. Maybe something.
Yes, it would be interesting to look at. Yes, I don't remember how exactly the solution to the equation looked like, so I can't really figure out if this would work similarly in the higher dimensional case. So, yeah, but yes, it would be interesting to look at.
One could also consider the case with singularities of boundaries. In other words, consider manifold where you have like a geodesical incompleteness, so not for each point. You can find the geodesic, so
what does it mean, geodesical incompleteness?
with each point is a geodesic. So in particular, it can happen if you have some singularities. Or if there is something with the boundaries. With boundary, it cannot do it. Somehow, like for natural extent.
Yes.
But this must actually happen with this 1 over R, isn't it? This must happen with this 1 over R example. It is incomplete because you cannot continue geodesics into this non-defined area, into the non-defined area.
Okay, there is one question from Thanasis. So please unmute yourself.
Hello. Yeah, first of all, a very nice talk. Thank you. It was a very nice presentation. I have a comment actually. So the definition that you gave for the Lie derivative of the connection has been used actually several years ago by Stienon, Mehta, and Zhu in the context of differential graded manifolds. And it's in this context, it's called the Atiyako cycle of differential graded manifold. And the formula that you had, the red formula with the second derivative, the curvature and the torsion, is also a very natural formula that comes out from the Atiyako cycle. In fact, I gave a talk in February there, and some people will remember actually exactly the same formula. That's actually very interesting because this is in a different category. It's in the DG manifolds. So it could be interesting maybe to understand the relation between the two. I can send you the references if you wish.
Oh, yes. So thank you, I guess, for the comment. I was not aware. Can you repeat the name once again, or under which this is known?
Atiyako cycle of a DG manifold.
Ah. Oh, yes. I was not aware of this. I have seen the formula. I have seen it for the case of vanishing torsion only, and my supervisor sort of directed me in the direction how to formulate it also for the case with non-zero torsion possibly. So yes, I was not aware of this. So yeah, thank you for.
Yeah, it's very interesting. Actually, it's exactly the same formula, so it's very nice. And yeah.
Yes.
There is also a Czech Austrian school of natural operations in geometry. So they were searching for many for categorification of derivatives of tensors. I don't remember the collections, but there's a quite known book for categorical geometries, if I may say it in this way. Kolář, Slovak, Michal Kolář, Slovak. Michal is from Vienna, Slovak is from Brno. And then there were really, it was It's called natural operations in differential geometry. Maybe they are analyzing it under another names.
Yes. So maybe you can repeat to me the names afterwards.
Natural operations in differential geometry.
Bring back to the example of this inverse power of R. So the case M of 2 seems to be certain.
Oh, yeah, yes, I remember.
That's one of the terms in the one of the terms.
Never mind, I can do it this way, I guess. So you want to go back to the equation itself?
Yeah, over here. And also especially because your symmetry U was dependent on the
Yes.
T. So you will be having only a rescaling in the radial direction. So what was the interpretation of this case?
Oh yes, I remember. I was thinking about this before, but I don't remember what the outcome was. Actually, my supervisor told me something about this. So the M equals 2 case would be the like quadratic potential, and yes, I don't remember. I'm sorry, but yes, it actually made sense once he told me, but I don't remember what exactly the point was. But yes, it made sense that it was in that case only the spatial expanding of the space time. I'm going to try to remember. Maybe I can refer back to you.
So in general, the premise of Newton Cartan approaches to solve an underdetermined system of PDEs by just composing extra symmetries or extra conditions. So if you go back to this one.
One more page.
Maybe two more.
Okay.
To the general setup for Newton Cartan. Oh yeah, over here.
This one?
Yeah, so 18 is an underdetermined system of differential equations, and so so people are seeking for connections which will satisfy equation 18, but they will be but it will be underdetermined, so to speak. So
Oh, in what sense underdetermined?
so so equation 18 puts only n determines only n components of your connection of your historical symmetries. Right, so there will be more of them. So the rest of them is up to us. So we just impose some symmetries. And
so in the case of vanishing torsion, these guys are non-zero only, and the others vanish.
okay. So you also can not mention. Sorry, vanishing torsion.
Yeah, yes, I should have put it in there, but I guess I forgot, so I just mentioned it by saying it. But yes, once you consider the 17th condition and the zero torsion, it becomes uniquely defined by only these three non-zero coefficients.
Isn't the M equal to K is related somehow to, let's say, the period of certain trajectories when you rescale it by the radial direction? So by simply rescaling, in that case, you have the trajectories at the same period. Since, well, for example, in the image you were showing where you have the Earth moving around, in this case, you are not rescaling on the time direction. You're just rescaling on the radial one, and so let's say as further you go, the stronger is your potential, and so.
Yeah, so this potential would work kind of like a pendulum style thing. Yes, so I guess
I would say it's something like that. So the period you have for those trajectories does not depend on rate, doesn't depend on rate of scale. That's my interpretation of M equal to.
Yes, that would make sense.
Maybe I just have a question and remark that I like the talk as well. And have you checked whether, assuming your connection be a Levi-Civita one, reproduces killing equations? Or
Actually, so for the Levi-Civita case, you have you have the tensor, right? This is what I call it, and so since you have also a metric, you can lower the index. And actually, I think this is not directly equal, but once you play around with the lower index case, you can express the condition for symmetries in this way. This is the metric. Yeah, so this also allows you to see the relation between the symmetries of the metric itself and the connection. So if this inside of this becomes zero for like unit fields, obviously these are also symmetries of the connection, but there might be more symmetries of the Levi-Civita connection than of the corresponding metric generating the connection itself. So yes, and also if this is like constant times these are conformal symmetry that we this also then is satisfied because but this has to be a constant. It doesn't work for functions. Yes, so
looks very powerful.
yeah.
Okay. Okay. Any other question? Okay. If not, I would like to thank the speaker again.